Ladies, today we're going to talk about counting principles, and tomorrow we'll use what we learn about counting principles as we learn how to calculate probability of certain events. So let's take a look here at goal 1. We want to begin by solving simple counting problems. So I started off with 2 examples, and I just want to see how you would do with this and then discuss it. So 12 pieces of paper are numbered from 1 to 12 and placed in a box. 1 piece of paper is drawn from the box. Its number is written down, and the piece of paper is returned to the box. Then a second piece of paper is drawn from the box, and its number is written down. Finally, the 2 numbers are added together. How many different ways can a sum of 6 be obtained? So let's think about this. What are the different values we could draw the different pieces of paper and come up with the sum of 6? Well, I could draw a piece of paper with a 1, and I know that its partner would have to be a 5 in order to have a sum of 6. If I drew out a 2 the first time and then returned it to the box, I would have to draw a 4 the second time to come up with the sum of 6. If I drew a 3 and returned it to the box, I would have to also draw a 3 to come up with a sum of 6. If I drew a 4 and returned it to the box, I'd have to draw a 2 the next time. If I drew a 5, I would have to draw a 1 to come up with a 6. If I drew a 6 or higher, I would not be able to have a sum of 6. So I can see that I have 1, 2, 3, 4, 5 different ways that a sum of 6 can be obtained. Let's try a similar scenario in example B. 12 pieces of paper are numbered from 1 to 12 and placed in a box. 2 pieces of paper are drawn from the box at the same time. The numbers are written down and totaled. In how many different ways can a sum of 6 be obtained? Okay, so let's go through that same process again using some logic. If I drew a sum of 6 at the same time, I could draw a 1 and a 5. I could also draw a 2 and a 4. But in this case, it's impossible to draw 2 3s at the same time because there are 12 pieces of paper and each are numbered from 1 to 12. So I cannot have 3 plus 3 in this situation. I can draw a 4 plus 2 and a 5 plus 1. And again, anything 6 or higher is not going to give me a sum of 6. So in this case, there are 4 ways that I can obtain a sum of 6. What I'd like for you to do in C is determine why the 2 scenarios had a different number of outcomes. Take a moment and jot something down. Well, let me share with you what I came up with. I said that scenario A used replacement because each paper was returned to the box before the second paper was drawn. Therefore, this allowed 3 plus 3 to be one of the ways that a sum of 6 could be obtained. The user drew a 3, returned it to the box, and drew a 3 again. Scenario B was without replacement. Therefore, the first paper was not returned to the box before the second paper was drawn, and this eliminates the possibility of 3 plus 3. So when you are comparing a scenario with replacement to a scenario without replacement, make sure you notice that it will change the number of ways that an outcome can be completed. Let's take a look at goal 2. We want to learn how to use the fundamental counting principle to solve more complicated counting problems. Now we're going to take this counting problem in scenario A and try to complete it without using the fundamental counting principle. So let's read. A probability experiment consists of tossing a coin and then rolling a 6-sided die. How many different outcomes does this experiment yield? Well, one way I can figure this out is to draw a diagram. You may have heard of a tree diagram before. So with the tree diagram, let's decide whether we're going to start with the penny or the die. And it doesn't matter. I'm going to choose that we'll start with the penny. So let's say, well, and it would make sense because the experiment says it consists of tossing a coin and then rolling a die. So if we take our penny, or any coin in this case, and we roll it, we know that we have two outcomes. We could have a heads, or we could have a tails. Well, when we roll the die, we know that we have 6 possible outcomes. So if we roll a head, we could roll, if we flip a head, we could roll on the die a 1, a 2, a 3, 4, 5, or a 6, which would give us a heads and a 1, a heads and a 2, a heads and a 3, heads and 4, heads and 5, or heads and 6. If we flip a tail, we again could still roll a 1, 2, 3, 4, 5, or 6. So we could have as an outcome a tail and a 1, tail and 2, tail and 3, tail and 4, tail and 5, and tail and 6. So if we count those up, we have a total of 12 different possible outcomes. Now, making a tree diagram can be a lengthy way to find the number of outcomes. So let's see what the fundamental counting principle tells us. The fundamental counting principle is the number of ways in which a series of successive things can occur, and that is found by multiplying the number of ways each thing can occur. Let's take our example from above. If we flip a coin, well, we have the outcome of either a head or a tails, which is a total of 2 outcomes, or 2 ways to get our outcome. The second thing after we flipped the coin was to roll a die. And you know, when we roll a die, we could have the option of 1, 2, 3, 4, 5, or 6. So we have 6 ways for that event. And if we use the fundamental counting principle, the number of ways in which a series of successive things occur is found by multiplying the number of ways in which each thing can occur. So flipping the coin can occur 2 times. Rolling a die can occur in 6 different ways, and the product there is 12 different ways, or 12 different outcomes. So I hope that you see how the fundamental counting principle is definitely a more efficient use of time than making a tree diagram. You try example C, turn the screencast off, and then turn it back on to check your work. So I have 3 different things here. I have the manufacturer, car size, and the color of my car. I have 3 different manufacturers to choose from, 2 different size cars to choose from, and 4 colors to choose from. So if we multiply the number of ways each of those things can occur, we could come up with 24 ways we can purchase a car using that information.